Now we're going to take a more deeper look into one specific algorithm called Gauss-Seidel and see first how we can improve its locality, and in the next video we'll look at how to parallelize it. Gauss-Seidel is the same algorithm that will be used in the third lab. So what I'm going to tell you about here there is a longer explanation in the paper in ICS. Also online there is a version at the HPC Wire called Finding a Door in the Memory Wall. So when you design an algorithm for high-performance computing or for supercomputers, in the past you've been concentrating on two different criteria. One is that you would like to maximize the scalability or the parallelism of the application. And the other one is that you would like to minimize the communication, how much these parallel processes or threads need to send data to and from each other. That was in the past when you wanted to scale to thousands of processors on one of these supercomputers. But if you look at what is important when you would like to make an application run well on a single multi-core chip, first of all, communication is fairly cheap as long as it's on-chip communication. So cache-to-cache transfer is not all that expensive anymore. The scalability needs are quite moderate. So if you have 10 or 20 cores, well, you need to find 10 or 20 different parallel threads that can execute at the same time. You also know that there are limitations on these chips. So cache capacity per thread is quite small. And we also know that the memory latency and or the bandwidth to DRAM could very likely become a bottleneck for these kind of chips. Another way to look at it is if you hit the bandwidth wall, so you're running at the maximum bandwidth capacity of the chip, this becomes a serialization component, and you can bring out your knowledge about Amdahl's law and see what serialization will do to the speed up of your application. So it's designing a algorithm for multi-core is actually a different task than just getting the maximum amount of parallelism as the theoretical work has been looking at before in finding good HPC algorithms. So data locality is important. That's what you're going to see in this example here. So the example we're going to look at is the algorithm Gauss-Seidel. And I'm trying to show in this picture what Gauss-Seidel actually is doing. So we have a matrix here, and in Gauss-Seidel we walk through this matrix row-wise, and we update each point in this matrix by calculating the average between its value and the value from all its neighbors. So the number you see in the circles here are what iteration this belongs to, because you're going to do this many times. You're going to sweep through this matrix many times and make this update over and over again. As it says in the algorithm down here, you're going to loop and update all the points with the average from neighbors, and then at the end, when you come down here, you're going to make a convergence test to see if you're done. If you're not done, you're going to go to the beginning again and start looping through. So the symbols I'll use here is the red arrows that shows where we have a data dependence. This is where we actually need the value above us and to the left of us to be updated before we can make the update to this yellow cell over here. The grayish or whitish arrows, they symbolizes data that we can read without any data dependence. So this is where we have the old value. So the value to the right of us and below us can very well can contain the old value from the previous iteration. So there is no data dependence here. This array is often large. I'm going to show you two-dimensional matrices here, but in the real world they may actually be three-dimensional, actually even higher dimensions when you do this calculation. So it's not very likely that this matrix will fit in the cache of your processor. So every time you come to the end, you figure out that you need to go to the beginning again. You're going to probably run into cache misses when you access these data again. Another problem here is that the data dependence. So we have dependence between values, and that can limit the kind of parallelism we can create here. We really need to update the left element and the top element before we can do this element. That means we cannot work on the top element and the left element in parallel with working on the yellow element. There has been some tries to still get some parallelism out of this algorithm, and that's often referred to as sort of a wavefront way of getting parallelism. So what you have here is a way of updating this matrix where you use n different threads, and all of these threads work synchronously with each other. So they keep this wavefront here, and they work on a diagonal of this matrix. Instead of just working row-wise, they work diagonal-wise. And as you see here, we have data dependencies, but we still have exactly the same data dependencies, but we are obeying them. So we have already updated the element. For example, if you look at this update here, we have already updated the top element and the left element. So this parallelization is actually a correct one to do. So we have a parallelism here. We can have up to n threads working at the same time, so that's good. Drawback, we have a pretty bad load imbalance. Thread number 1 and thread number n will only have one cell to update in their life. Well, while the thread in the middle, the thread n-2, will have most work of all these threads. It's also a large synchronization need, since we have to make sure that all this wavefront is propagating synchronously with each other, so we can obey all the data dependencies. So you sort of have to insert a barrier at the end of each of these diagonals that have been updated. When I updated the yellow diagonal, we have to put in a barrier here before we start to work on the next diagonal. So lots of communication between the threads. And there's also quite nasty data sharing going on here. So if you see the layout, cache layout here, in this picture, it's a row-wise layout of cache lines. That means that a thread that moves in the diagonal is going to touch a new cache line, read data from new cache lines, as well as writing new cache lines every time they move in the diagonal. And that is not ideally what we're looking for. Instead, the state of the art in the literature for how to make this parallelization is a technique called red-black. So in the red-black scheme, we have colored every element of this matrix in black, red, and so on. And then the algorithm is that first we update all the red points of this, then we update all the black points of the matrix, and then we do the convergence test. So what's the nice property here? Well, the nice property is that, as you can see, we have no red arrows. There is no dependence to any other updates that happens concurrently as you update. For example, when you update the red elements, they only read data from the black elements. So there is no data dependencies within the red updates and within the black updates. However, you should also note that we have changed the algorithm slightly here. Numerically, this is not equivalent to the algorithm we had before. So that means that the convergence test that we do at the end here is not going to have the same convergence rate as the previous one. It may be better and it may be worse. But still, this is regarded as a good compromise because of this nice property that we don't have any dependencies to any other concurrent updates. The way we can leverage this is that it's trivial to parallelize this algorithm. Since we don't have any dependencies between the red updates, while we do the red updates, we don't have any data dependencies. That means what it actually can do, update all the red the entries in the matrix, we can be updated in parallel. What I'm showing here is just a parallelization of 2, where we divided the work between core 0 and core 1. And the way you do that is in parallel, update all red points, and then you have a barrier to make sure that everybody's done with that, and then in parallel, update all black points. So even though I'm only show 2 cores here, the amount of parallelism you have in this algorithm is n squared over 2, since you can work on half of the elements, which is you can work on all the red elements at the same time in parallel, and then you can switch over and work on all the black elements. There is also very limited communication. So if you have this kind of parallelization between core 0 and core 1, the layout of the cache lines are like this. So there is very little communication going across this dashed line here between the cores. It's just read communication. So in order to update this black entry here, you will need to read the value of this red entry here, for example. So there is communication going this way, but we have a very good spatial locality in that kind of data transfer. You transfer the cache line once per iteration, and then you can leverage all the entries of that cache line. So we're done. Look at this. We have really good parallelism, and we have very small amount of communication. There's just one problem that remains, and that problem is that we get very poor performance. So look at this. We go look at the performance improvement, where we go from 1 to 2 to 3, and so of course we sort of level off here. So in spite of this theoretically very nice algorithm with lots of parallelism and very little communication, we still level off here. So can you explain what's going on? What is a plausible explanation for the limited speed up we see here in spite of this almost perfect algorithm? So it is that the many cache misses causes the execution to be limited by DRAM bandwidth. So we are already at 2 cores. We are very close to the amount of data we transfer per time unit is very close to the absolute maximum here for this specific chip. And that means that as we add more and more cores, yes, we have more parallelism. They potentially could do more work, but it's all going to be serialized by how much data can be transferred from the DRAM to the multicore. And actually, if you think about it, the red-black algorithm is much worse than the first algorithm in the respect of the amount of traffic you need to send to DRAM. Because for each iteration, we're going to sweep the matrix twice. First, we're going to sweep it to do the red updates, and then we're going to sweep it once more to do the black updates. So we're going to get actually the twice amount of cache misses for a naive implementation compared with the first version of Gauss-Seidel as we looked at. So not only having not managed to remove the problem, actually made the problem much worse than it was before with the red-black algorithm. So what to do now? Well, we're going to go back to the drawing board, and we're going to see if there is a better way to implement this algorithm. And we're going to do that by focusing first on creating good data locality. And after we've done that, we will try to get some moderate amount of parallelism in the following video. So what we'll do here is to have an algorithm that looks very similar to the first one, which is what's called the natural order. That's what the first version of Gauss-Seidel I showed you is called. So we'll walk through this array, and we will have the kind of updates where we have data dependencies from above and from the left, and no data dependencies from the right and from below. But we will work inside a active region at a time. So the high-level description of what we're going to do is we're going to loop over the matrix. And when you loop over the matrix, we're going to update all the points in the active region, but only in the active region. And then we slide the active region down. Okay, we're going to do that until we've operated on all on the entire matrix. So this is what it's going to look like. So the numbers here, 1, 2, 2, 3, 4, 4, that corresponds to the iteration number. So we see we have already done an update to the lowest level in this active region. And then we keep moving forward. So now we made updates to the next higher row here. So those iteration numbers went from 2 to 3, and we keep working until we come to the end of the active region. And now we have updated all the elements of the active region. The cache layout is as we talked about before. So these updates we make here, it will get very nice spatial locality, so that's good. Active region is the region that marks the elements we're working on concurrently. So these are the elements, all the rows of the matrix that's being worked on concurrently. Once we updated all the elements, you can see that the top iteration has been updated 4 times. So iteration number is 4 here for these elements, which is the same for the elements above it in the region as well. So now we're sort of done with the top line of this. So what we're going to do is to slide the active region down, and we're going to apply the same algorithm again. Update all the points in the active region. So we're going to keep working ourselves up like this again. Until we reach the top line, we updated all those elements, then we're going to slide the region down again. So by doing it, this kind of algorithm, we create locality, we create data locality. And after we have swept this matrix once, so we've had all those terrible cache misses that we will get once for every cache line in this region, we have actually updated 4 iterations of this algorithm. So we've done 4 iterations, then we do the convergence test. Maybe we will have done a couple of iterations too much. Maybe we needed to do 11 iterations, but since we do 4 at a time, it's not until we've done 12 iterations that we'll do the convergence test. But that's okay. There is such a small cost of doing some extra iterations while you have this piece of data in this block. Because if you design this block, this active region, such that it fits in your cache, that means that we're going to get some kind of blocking properties similar to the blocking. We looked at the blocking for matrix multiply. This is a similar thing, but it is sliding blocking, or sometimes we refer to this as temporal blocking, where we slide the block down nicely over the matrix instead of dividing the matrix hard into some blocked regions. So this should clearly give a much better locality for our accesses. And we can see on this graph here that shows how much DRAM traffic it generates. So this is the DRAM traffic. It says how large fraction of memory operations will miss in the cache as a function of cache size. So what you can see here is the red-black is the top one. It has 3% fetch ratio, so this corresponds to bandwidth needs. If you have the natural order algorithms with the blocks, which corresponds to a block size of 1, this is how much traffic you will generate. Block size of 2, yellow one, and then the turquoise is the example I showed you, block size of 4. So I see the amount of traffic generated here compared with the traffic generated by the red-black is quite a lot less. So this looks like a very nice property. The larger blocks you have, the lower is the traffic to DRAM. However, there also seems to be some kind of negative effect going on. The larger the block is, for smaller caches, the higher is the traffic. See here, for a 512 kilobyte cache, the traffic generated if you have a block size of 16 is larger than the traffic generated if you have a block size of 8. So the question is, why is this? Why is it that traffic decreases as we expect when we increase the block size, but for small caches we can see that the traffic increases? Well, so it's that the larger block you have, the larger active region you have, if you make that active region too large, it will no longer fit in the cache. So this wall here, for every time we make the block larger, this wall that sort of climbs up here, this ski hill will keep moving to the right. So what you have to do here, as we did with a matrix multiply, is to find a block size which is corresponds to the size of our caches where we want to create this kind of locality. So that's the creating locality in this algorithm. And next video we look at how this improved data locality algorithm can actually be parallelized as well.